Regulation of insulin secretion. So what regulates insulin secretion? Meals are one of the biggest stimulatory events. A meal is thought of to be very important because you're going to start getting blood glucose after a meal. Therefore, you'd want insulin levels high to drive that glucose into cells. So having high insulin levels after a meal makes a lot of sense. There are a few agonists that we'll go through one at a time, such as neural ones, other ones from the GI system, as well as from the pancreas. There's a few antagonists that we need to deal with first, and that has to do with norepinephrine, and norepinephrine usually is released during a sympathetic stimulatory event, as well as somatostatin. If you remember back to glucagon, you can see that somatostatin not only inhibits insulin secretion, but also glucagon secretion. Now let's look through the meal in a little bit more detail. What about a meal stimulates insulin to be secreted? Glucose is probably the biggest stimulant, although amino acids and free fatty acids can also be part of the process. But let's talk through glucose. Glucose enters a beta cell via GLUT2 receptor, following a concentration gradient. It then undergoes metabolism and ATP is produced. That ATP that's produced is going to bind to a potassium channel sensitive to ATP. That closes that channel, and as that channel closes, potassium is no longer allowed to leave the membrane. If potassium, which is a positively charged ion, is not allowed to leave, positive charges start building up within the cytosol of this beta cell. What does that do? It starts to depolarize the cell. As that cell depolarizes, it's eventually going to reach a threshold for calcium. This L-type calcium channel will then open, allowing calcium influx into the cytosol of the beta cell. It is that calcium that will have vesicles that contain insulin and C-peptide to dock and fuse into the cell membrane of the beta cell. It will spill its contents, and that will then be picked up by the interstitial fluid, the blood, and travel around in the circulation. Neural agonists are also involved. This is especially acetylcholine, but other ones such as vasoactive intestinal peptide also can come into play. You notice here that we have norepinephrine here as an agonist, and you're going to say, why? You just told me norepinephrine was an antagonist. I did. But this is now responding to a beta adrenergic response. That is an agonist as a beta. When it binds to an alpha cell, it's an antagonist. So here with the cholinergic response, you bind to acetylcholine receptor. These are G protein coupled receptors, and as they're engaged and transduce their signal, they will activate an enzyme called phospholipase C. Phospholipase C will make IP3. IP3 then goes to the endoplasmic reticulum and releases calcium out of the endoplasmic reticulum. This calcium further helps the vesicles that have insulin and C-peptide to dock and fuse and release their substance. Now, besides neural agonists, there are a few others, such as GI agonists. One here, cholecystokinin. We also have glucagon-like peptide. And here we have GIP. GIP is also an agonist. It works through another receptor that's also G-coupled protein receptor who stimulates adenylate cyclase now as the enzyme. That increases protein kinase A. Protein kinase A also facilitates this docking and fusing of the vesicles to the beta cell wall, which then goes into the interstitial space and picked up by the blood. Interestingly, one pancreatic agonist that we haven't talked about is glucagon. And you're going to say, similar to the norepinephrine, hey, glucagon is supposed to be the opposite, right? It is antagonizing most things insulin is doing. Yes, that's true. I know it's true too. But as glucagon is released, eventually it's high enough levels that will stimulate insulin secretion. This is probably a negative feedback mechanism so that you can predict when blood glucose levels are going to be high, and then you'll want to drive them in. So glucagon is considered a pancreatic agonist. This just shows all of our agonists here together with meal constituents, our neural agonists, GI agonists, and pancreatic agonists. Hopefully you can appreciate from looking at all these is there's a lot of things that regulate insulin. That must mean it's really important. You don't get this many regulatory factors if you're not important. The insulin receptor. The insulin receptor is a catalytic receptor, and where two insulin molecules need to bind to it, and then it causes a catalytic response. This kind of response is going to enact a number of second messengers. So not just one, not just two, but a plethora of them. They are things like IRA, RAS, mTOR, MAP kinase. There are so many things that seem to be involved with the cell signaling for insulin receptors, it's almost hard to keep a hold of. But just remember that it's going to do a few things in a couple different tissues. And we're going to go through each one of those responses so you don't forget it.